everybody, welcome back after lunch break. Now this afternoon we will discuss some quite basics about the crustal thermal processes, but we also will take a look at some of the results we already know about the low-temperature thermochronology in Fennoscandia, as well as some of the, could we say, more younger geological history in the area. Now, the topics we're trying to cover, approximately at least, are here. So first of all, we speak about the heat flow and how to calculate the temperatures in the crust, and then we look at how different geological processes, in principle and in mathematics, how they affect the temperatures in the crust, like sedimentation and erosion, and we speak about intrusions, although intrusions are not necessarily a low-temperature thermochronological issue, but there are also features like extension and crustal thickening. Especially extensional processes in sedimentary basins are very important applications of low-temperature thermochronology. And then about Fennoscandia, we will have a discussion about the geological evolution of the area after the main rock and the crust forming orogenic processes in the Proterozoic. That means the times of various types of rifting, etc., and the Phanerozoic geological history of Fennoscandia, which is affected quite a lot, especially in the west, by the Kaleninite mountain building, but also the sedimentation in the surrounding areas. We will check the results by Glenn Murrow. He wrote a dissertation about 10 years ago, a little bit more, about using apatite fission tracks, uranium, thorium, helium, and various argon systems for low-temperature thermochronological modeling of Fennoscandia. And also there's a Fennoscandian-wide compilation of apatite fission track data, which is provided in a public dataset, and some results of that. I will also show some unfinished data about apatite fission track data in deep borehole. Plus, we will then finalize the discussion with the questions about the recent geological uplift and erosion in the last 10 million years in the area of Fennoscandia. Okay, now, first of all, the heat flow from inside the Earth. I have the tendency to use the old stick, if necessary. I'll try to point there as well. But the heat flow that we measure in geophysics is measured by two parameters. We need to measure the temperature gradient in the crust, which means making measurements in a borehole, and measuring thermal conductivity of the corresponding rock samples, that is typically the drill core samples or using the cuttings. And this is what it means. So the heat flow is determined as the product of these two variables which we measure. Now, the temperatures inside the Earth then depend on the conduction of heat, and this is described by this differential equation of heat conduction by Fourier, and it simply describes that the time-dependent changes in temperature are functions of heat sources in the medium plus the conduction of the heat in the rocks. Now, and this is the basic equation, but as it is just a differential equation, it requires solutions to get the temperatures. The parameters and the variables in the equation are, of course, capital T is temperature, small t is time, A is heat generation, which means typically radioactive heat generation from the decay series of uranium, potassium, and thorium. Lambda is thermal conductivity, and C is specific heat capacity. Now, these material parameters are related like this. So there's a parameter called S, which is diffusivity, and the diffusivity is the ratio between conductivity and the density and specific heat capacity. So this is the basic background, and now when we start calculating then the temperatures in the crust, we have to solve this differential equation with appropriate boundary conditions. Has any one of you ever been working with this kind of mathematics? Lotta has. Anybody else? Jorina has. Others? Yeah, and never been working like this. So the problem is that as the differential equation describes derivatives, and when we integrate these, the integration always will bring parameters which are called the integration constants. And they cannot be solved without us setting a set of boundary conditions. And in terms of geothermal calculation, the typical boundary conditions are such that we have to define what is the heat flow on the surface of the Earth and what is the surface temperature. Okay, these can come from simply borehole measurements, and then the mathematical solution in one dimension for the heat conduction equation looks like this. You need to know the surface heat flow, thermal conductivity of the medium, heat production, and the surface temperature. And this is basically an equation of the parabola. Now, you calculate that. You've decided your boundary conditions. Then you made the solution. Then you can calculate the temperature like in the crust. And then you can continue that into the mantle. That's one way. There's also another variant because sometimes the surface heat flow is not easy to determine without a bias. There's polyclimatic effects, there's groundwater flow, there could be topographic complications, whatever. And you can estimate that maybe we know better the mantle heat flow from other studies, or we make a good educated guess. Then the solution of the differential equation is a little bit different, but as simple to apply as before. And we simply would be doing the exercise this way, that we have the mantle heat flux, and then we have the surface temperature, and we calculate the geothermal. So here too, it has, of course, questions about how accurately we know all these parameters, etc. But this is the basic kind of a thing. And now we can, of course, make the thermal conductivity more detailed here. So it varies with different stratigraphies and rock types. And it can also be same for heat production and so on. But basically the calculation is like this. Now in low-temperature thermochronology, this kind of a mathematics and the physics provides you a way to calculate a forward solution. So what you get from a thermochronometer are times and temperatures. And then the question is that what was the temperature distribution with time and also with depth? Now, by the way, these solutions are very simple because we have ignored the time-dependent variations here for simplicity. But anyway, looking at the overall geological evolution, so everything in geology takes place in a Wilson cycle. So we have the plate tectonic processes, plus of course the superficial processes that are modifying the surface, like erosion, transport, sedimentation, paleoclimate, etc. So in a large scale, we have extensional processes, we have formation of oceanic basins, thinning of lithosphere, and really we have a mature oceanic basin with a spreading center in the middle. We have subduction systems, we have closure of the basing, and finally we have a continent collision. So, and all these involve changes in the crustal temperatures. And if you take a piece of rock here, mark that, and start following what would be its thermal history all the way in these processes, and you would be able to date that with a good thermochronometer, then you're well off to speak about the thermochronological history of a formation and your samples. Now, David already spoke about like problems about the topography and how deep and what time the topographic variations have an effect. In conduction physics, there is a simple estimator, which is the characteristic time of diffusion. So conduction is a diffusive process, and it has a characteristic time during which, if you have a layer with a thickness of L, here it's called lithosphere, it can also be anything else you're interested in or working on, and it has a certain thermal diffusivity S. The time T tells you simply an estimate of the time when the thermal disturbances have died out in the layer. So if I heat this table from other side with a new temperature now, so on the other side of that, the temperatures would be equilibrated after time T calculated with the thermal parameters and the geometry and the thickness of that table plate. So it's not an accurate value, but when your friends are asking you to give a solution for this kind of a problem, you can dig it out from your sleeve, like here, and quickly on the back of an envelope you calculate the characteristic time. And conversely, you can also calculate the characteristic distance. If you have 10 million years of time, how far does the thermal disturbance propagate? Now, here are examples. If I disturb thermally a lithosphere, which is 50 kilometers thick, it would take 80 million years for all the system to equilibrate. Actually, this kind of things mean that if you have plate tectonic processes going on, like in the oceanic lithosphere, it never reaches thermal equilibrium before subduction. It's always in a changing state, which is called a transient state in physics. What is running the thermal processes in the lithosphere? We need heat. Of course, there's the internal heat from inside the Earth, but in these Wilson cycle processes, there are different possibilities. First of all, we may have conduction. And most of the things we are discussing in this short course are conductive problems. We assume that heat transfer is taking place by conduction, and indeed its importance in crustal and lithospheric temperatures is very big. That's the number one factor in heat transfer. And the characteristic times can be obtained, as discussed a second ago. Then we have advective heat transfer, which means that there can be a fluid flow in the pores and fractures of the rock. So a flowing fluid always carries heat with itself. And therefore, it may create locally effects. Overall, it's considered to be small. But if there is a magma moving as intrusions or at great depth as underplaning effects or so, it can be a big effect. Now, advective heat transfer is also related to erosion and exhumation, but also sedimentation. Sorry, I should have sedimentation here, because that is also moving matter to a new place, and it's kind of a flow. That's locally also very weak. Now, then heat production. Now this is very important. Radioactive heat production of normal rocks is the order of 1 to 6 microwatts per cubic meter. So 1/1,000,000th of a watt per cubic meter. So it's a very small value in our everyday life experience. this lamp has something like 100 to 200 watts of power. So it's a million times bigger. But that's very important. And together with conduction and radioactive heat, they are the most important factors affecting the crustal geotherms. Locally, in metamorphic processes, you may have chemical effects, reaction energies, and also the latent heat. Especially when intrusions crystallize, there's an important latent heat effect involved, which should be involved in accurate calculations. But this is the kind of a sources of energy, and the most important source is the deep heat transported by conduction. Now, if you now take a simple academic example of what is the effect of sedimentation, erosion and uplift on a block of bedrock. It's shown here. You can see that first there is a steady constant gradient from the surface temperature T1 downwards. The layer has this thickness D, and we take try to follow like a point P here as an example. Now, if we suddenly uplift this block upwards without any erosion, you see now there is uplift, but there is no erosion. You have just a kind of a, this is my bedrock block. I raise it up to the ceiling, and what happens when you go up from the surface sea level to the mountains? What happens with the temperature? You all experience that. Like in the, yeah, it decreases. It decreases, yes. And typically there's an atmospheric lapse rate, which is something like, depending on the humidity of the air, it varies from 0.6 to 1 degree per kilometer, per 100 meters or so. Now, it means that when we take up this block to a higher level by the elevation difference h, the surface temperature is no more T1, but no, it suddenly drops to T2. But conduction in the subsurface is not taking place at an infinite speed. It's very finite, and the rocks are poor conductors of heat. Therefore, there is a transient equilibration of the temperatures to a new value. Would we wait for a very long time, we would finally have a new steady gradient starting from T2, and the heat flow would be the same, but the temperature levels would be different. But in real life, of course, this does not take place, because if you uplift a huge block of rock to several kilometers up, it starts to erode down. Because of this wearing and removal of material, so the real case would be, for instance, something like such that once you erode it back down to the starting level, and you have these intermediate geotherms, you would finally see the variations that are running like this. So depending on the thermal history and the uplift and the thermal properties, we will get quite a number of different possible geotherms. And this is possible that we can calculate many of these, but the inverse problem is the much more difficult. So you will have your rock samples that show thermochronological age, and you know the closing temperatures, you know the depth and the position of the sample, but it's much more difficult to say what is the thermal history of the sample. How did we come to that conclusion? Now, these heat transfer problems in sedimentation and erosion they are typically, if you ignore the heat production, they can be written like this. This is like a diffusion equation here. So this is like Fourier's second equation. But here we have an extra term which has the velocity of the medium. And this parameter variable u is actually the movement rate of the medium up or down. So it's the sedimentation rate, and then it is and solutions of this equation, which is quite a complicated thing. We're not doing that here at all. But you can see that we have analytical solutions available for a 1D world with a homogeneous properties. And this already is a relatively simple thing to numerize in any coding environment you might be using. So you can basically write this down and start calculating what would the temperatures be as a function of depth and time with these and these rates of sedimentation or erosion. There's also a solution for the gradient. So the temperature gradient can also be quickly calculated. You have this is not a difficult thing even in a scientific calculator to do. Now here we have some results shown for the gradient. Now this is the gradient effect in percent. So the original value of the change starts from here, and we have the erosion rate here as a parameter of the curves in millimeters per year, 10, 1, 0.1, etc. And here the time varies logarithmically. So it's in logarithm of years. So like this is 1,000, 10,000, 100,000, million, 10 million, etc. And you can read it from here that the effect is quite strong, and especially we are looking at times more between 10 to 100 million years since the erosion started. 10 million years would be here, and if we would have an erosion rate of say 1 millimeter a year, the effect on gradient would be around 40%. It really changes the surface temperature gradients in boreholes. And this is one of the things in heat flow studies when people are interested in a heat flow value to be used for lithospheric thermal calculations. They should be kind of a steady state estimates. And you have to calculate for this kind of a transient effect like erosion. And you can see the effect is strong. Now here is a range of values calculated for metamorphic temperature pressure estimates of Precambrian rocks here in southern Finland, and they suggest that at the end of the orogeny, the erosion rate was maybe something like a 0.1 to 0.4 millimeters per year. And if that is a kind of a normal thing in a big continental mountain system, it would indicate then in this time range since the onset of the system quite significant, several tens of percent of gradient effects. Okay, you change the sign of the velocity variable u to a -1, and you will get sedimentation rates corresponding. So this is just a reminder and an example that you can find analytical solutions. You don't always need to have a complete numerical solutions for everything. You can find out the order of magnitude effects already from analytical solutions. Then a couple of more, which are nice tools to play around. It's typical in this kind of a physical models that we make simplifications. So if we study the erosion and uplift in a steady state case, so we assume that the land uplift and the erosion have been going on forever as they are today. and we can define this kind of a boundary conditions. We can say that the surface temperature is 0, of course, and then the temperature at the effectively infinite depth, somewhere at very great depth, is given this value T infinite, and the solution is actually relatively easy. So it's not difficult. And the second case is that we have the same kind of a situation, but here we assign a certain temperature TL to a certain given depth. For instance, could be the Moho depth or base of the lithosphere, whatever. And now, with this kind of a steady state models, once again, you can see how the things vary. Now, note here the scale of the depth goes to 1,000 kilometers. It's really deep here, and the model is such that somewhere here at very great depth we have temperature at 1,000 degrees, and we vary the erosion rate like this. And you can see, if you erode very quickly, what you expect to see here would be that in the near surface layers you would have a very high temperature gradients. Just like what Dave said before lunch, because of the high rate of erosion, we are bringing a lot of hot material and rapidly close to the surface. So the gradient must accommodate, and it accommodates by increasing to very high values. Here's the other case. We have 1,000 degrees at 100 kilometers, and once again you can see quite some variation. This case would be with no erosion, the 0 rate, and 100, 1,000, 10,000, and quite some changes are taking place. So this kind of a quick calculations give you an order of magnitude what to expect. In terms of thermochronological estimations then it would be quite important to know that if you have a borehole sample, say it comes from 5 kilometers, it has an avatar fission track age of 10 million years. So it would represent maybe a temperature something like 60 to 120 degrees. So it's completely different question depending on what is the rate of erosion. But these are kind of a forward models of the temperatures with different solutions. Now, if we look then a case of having a sedimentary cover on top of a crystalline rock, which is the case, all the Baltic countries are such, or most of the Russian platform, and all over the globe. So in the first case, we have the kind of a comparison geotherm, and we have two samples here at the depth A and depth B. And what happens here then in case B is that we are adding some sediments on top of this case. Now this is kind of a crystalline environment. It is a certain thermal conductivity. And what happens then when we add this layer of sediments? Okay, this geotherm is actually a kind of a push down by the thickness of the layer of the sediments, and then after a while the system, because of the heat, is equilibrating in the system. According to the geophysically prevailing boundary conditions, there's heat coming from the depth and the surface temperature is kept at a certain value. So the system will finally develop into a new equilibrium. So the sample in A will finally be in A, comma, at a deeper value and a higher temperature. Now this is the case that the thermal conductivity and the heat production of the sediments are equal to that of the basement. But now the thermal conductivity can create an interesting trick here. Because you can think that as the heat flow is determined as the product of the thermal conductivity and the temperature gradient. If you keep this constant, so heat flow is constant, and you increase or decrease thermal conductivity, what happens with the gradient? Of course, it varies inversely. When conductivity increases, conductivity decreases, and vice versa. So, if we happen to add here sediments which have a lower thermal conductivity, but the heat flow, of course, keeps the same in the final steady state. The heat flow is the same. It means having a lower thermal conductivity means that the gradient must be higher. Now, the crystalline rocks have a thermal conductivity of about 3 approximately, but if you're adding sediments, the sediments are porous, the pores are filled with water typically, could be hydrocarbons, could be gas. Water has a low thermal conductivity of 0.6. And if the sediment consists of, say, shale, it has low thermal conductivity because it's clay minerals, so they have a conductivity of 2 or something like that. As a result, the sedimentary rock has a low thermal conductivity, and the resulting geotherm shows a higher temperature line. And the final geotherm would look like this. So the sample from A is now jumping into A dot and A comma. But in the case that instead of sedimenting shale, we would have a quartzitic sandstone. Quartz is a very common mineral, and in sediments, it's in a very well sorted final end product sediments, we get quartz sands. When they lithify, we get quartz sandstones. And quartz is a mineral with a conductivity of about 6. It means that the conductivity in this kind of a sedimentary rock would be much higher than in the shale case. But because of this dependence on between thermal conductivity and temperature gradient, you might have actually much lower temperatures. And the final case would be like this. So the sample which is now originally at A will be projected to the point B. And imagine that your thermochronological project is based on samples that you're actually taking from deeply eroded crystalline rock. And with metamorphic techniques, you're able to find out the pressure, it is the depth, temperature, time, path of the samples. So you have actually no way of understanding why this has taken place if you don't know anything about the sediments that existed on the surface. So this is just to remind you of with a simple example that the problems are non-unique. The thermal history and the geological history behind a thermochronological result, which could be like this, that we can find this with our analysis and laboratory work doesn't actually solve the exact thermal history. That was a case where everything had equilibrated to steady state. So time was not a problem. But here the time is a problem, meaning that we have an initial geotherm, and when we sediment material on top of the crystalline, we can then, with numerical models here, this is by Chapman and Furlong, and we can calculate the thermal history of a single piece of rock at some depth, like here, originally at 10 kilometers, etc. And we have what's going on. It's 10 kilometers of sedimentation and subsidence during 20 million years, which is kind of a normal evolution in a sedimentary basin. And we can this is the time of the sedimentation and subsidence, and then everything stays at the depth level it has attained. And here you can see the warming curves for different layers. So the thick line corresponds to this thick line in the other graph, etc. Now you can see what happens here is that because of the sedimentation, the samples experience an increase in pressure. Pressure is immediately created in rocks if you add load on top of them. But the thermal equilibration takes more time. But after the adding of pressure, there will be the warming up because of the added heat production and the layer on top. These 10 kilometers of sediments on top. As a result, we will see this kind of a metamorphic evolution of the different layers. And given that we have suitable metamorphic paragenesis, and like here with the aluminium silicates, kyanite, andalusite, sillimanite, you can see that in thin sections, and you can model the thermal evolution with the help of the geological evidence. If you have any questions, don't hesitate to ask. I do not guarantee that I can answer, but at least I try. Please, if there's anything that comes to your mind, just make a question. Okay, so that's kind of a things take place in the sedimentary environments. Now, then some words about extension. Now, extension is an important part of the geological evolution and plate tectonics, and we can speak about two types of extension. They can be either pure shear or simple shear type of processes. So this relates how the matter is deformed under the extensional stress. Now, in a pure shear, the lithosphere is behaving like as if it were a kind of a molding clay or a kind of a elastic rubber sheet. When you extend that, it thins. Whereas in the simple shear, the extension is taking place with the aid of a low angle fault. So you can pull these two blocks apart by moving them along a low angle fault. Now, of course, the real geological world is perhaps a combination of these two. But in case of later geological investigations, in this case, if it is a pure shear, you will never see any after erosion. You will never see any high pressure rocks on the surface. Whereas here, in a simple shear case, you will see relatively high pressure rocks thrusted to the surface. There's a wide literature about the tectonics of this extensional shearing. Now, I will quickly remind you of the Mackenzie type models. Dan Mackenzie was one of the, and is one of the fathers of plate tectonics, and he created a number of very elegant innovations in using physics to plate tectonic problems. One of them is the extensional pure shear model and its thermal consequences. There was a time when I was much younger, and there were sessions in like AGU and EGU conferences where everybody was doing extensional modeling, and 2/3 of the people were using a Mackenzie model or an elaboration of a Mackenzie solution. This is due to the fact that say 30 years ago, computers and the computing capacity was not that fancy as it is today, and this kind of an analytical model provided a direct insight into extensional processes, and it was so nice that it was used by oil companies for estimating the thermal history in sedimentary basins. Now, what takes place in a Mackenzie model is a pure shear, and there is a instantaneous extension, and then we take a look at what happens thermally thereafter. There's an extension factor beta, which is simply the ratio between how thick was the lithosphere before and after extension. And typically this in intracontinental basins, the beta has a value between 1 and 2, but if you go really to offshore systems, it can extend up to 5. Now, this is how it looks like. You have an initial situation, you make this pure shear extension. Just geometrically, you thin the crust and the mantle by the corresponding amount, proportionally. And what comes after that would be that you would have the first theoretical geotherm, which is assumed to be straight on through all the lithosphere, and then there is an asthenosphere, which is a constant temperature. And then you have these transient stage like the G2 immediately after the extension, and then in the case later after when the system has cooled down, so that the crust remains in a thin case, but the mantle part of the lithosphere thickens because of the cooling. So the asthenosphere temperature is made deeper and deeper. Now, so this is how it goes. So this looks even too simple, but it works relatively nicely. So what you're actually doing for the geotherm is that you just simply change the scale by the factor beta, and you get a new value, then you get a new value for the temperature gradient, etc. And what is done then in the Mackenzie solution is the calculation of the temperatures for the transient phase. And we are not exercising this in too much in detail, but the point is that we can calculate with this then the temperature in the crust as a function of depth and time, and we can calculate also the heat flow at the surface. And what happens in this kind of a case is that here we have the non-dimensional heat flow. So the dividing part is the initial heat flow Q0, and you can see that immediately after the extension you get a very high heat flow because the asthenosphere is brought very close to the surface and the gradient increases, and that increases the heat flow. Then there is a equilibration with time. Now, if you have a borehole drilled into a sedimentary basin, and you have rocks which can be stratigraphically identified their age units, and then you can take like apatite fission ages of those using apatite separated from the samples. You will get information about the cooling history of the drilled column. Then this can be directly compared with the this kind of a extensional models. The model also calculates the subsidence and etc. Now, but extension is always a part of the opening of a basin. But if you look at the topographic maps of Europe and say Greenland, what can you see? What is an interesting thing? You can see that the topography, when you come to the shore, it's not even. It's not like the Finnish peneplain, which is practically about almost on the sea level, very old, very deeply eroded, very even topography. But instead, in Norway, you have nice, beautiful mountains to about almost 2 kilometers, something like that. When you go to the Greenland eastern coast, you have the same there. So when the Atlantic opened, there was of course extension, but the extension probably was not a pure shear, but maybe it was a kind of a simple shear. And this is one of the kind of an ideas to understand why an opening basin creates a mountain range on the coast. Is the kind of an idea that if you have this kind of a fault, where the movements are shown by the arrows, so this is extended by pulling them apart and then sliding along the fault, you will actually create a structure where the thickness of the crust and the thickness of the mantle part of the lithosphere in sections when you go from the basin to the continent is quite variable. If you have a low density crust and you have the asthenosphere material here, then you have the high density mantle part here. It means that here the density of the lithosphere would be normal. But what happens if you decrease the density of the lithosphere? Does it keep at the same depth level? No, it comes up. It's like a buoyant piece of ice or wood in water. It comes up. If you thin the lithosphere by removing by this ball that extends all the way down to the lithosphere, you would have a very lightweight part here, and that would actually pop up as a mountain range, and it would have an age which is nicely correlates with the opening of the basin. Now, this is one of the big questions in Fennoscandia. Why do we have these mountains in Norway? The rocks are about 360 million years old. They should have been eroded back to the sea level already. And there are two schools. One of them says that, oh, yes, they are. The mountains are old. But then there is another school saying that, no, the mountains are young. And if you go there and look them, you have very steep slopes and relatively young looking mountains. Now, and this is one of the questions that people try to solve then by using thermochronological methods, appetite fission tracks and that kind of quantitative approaches to the problem. Dave.
I have a question.
Please.
I guess this picture is meant to show how rift shoulders uplift or something like that. In the case of the Atlantic, for instance, would we expect that the mantle lithosphere would have thickened again? I mean, like, obviously the picture here is sort of some kind of cartoon version of showing how the crustal thickness is, the fraction of material that's crust is thicker than that fraction of lithosphere, so the average density goes down and it goes to higher surface elevations as a result. Do you know, like, I have to imagine that for the case for the Atlantic, that there would be time for the cooling to have led to thickening of the mantle lithosphere again, but the elevations are still relatively high. Is that?
I think the problem with this debate about the Norwegian mountains is related to the crustal roots. So if we have a crustal root, it creates this buoyancy, and you might have it there. Now, and if there's a very deep extending low density crustal root of say 10 kilometers or more, it really is not removed simply by erosion, so it could stay there. And that's one part of the story. But then there are these ideas that suggest that as the most of the thermochronological data suggests that we have young exhumation going on there, then the question would point more to this kind of an issue. But I would also ask, this is a very simple picture. If this is Norway, why in Greenland do we have the mountains? Because this would just say suggest the opposite. Or do we have kind of a tool, this kind of a shears there? But this, for instance, would be a good topic for a project, course project discussion. There's nice literature about this, especially in relation to the Norwegian case. Okay, we jump to intrusions, which have an important thermal effect locally. Intrusions coming from great depth and intruding into a host rock create their thermal anomaly, change in the temperatures, and with conduction models we can calculate solutions for these kind of problems. One of the basic ones is that you have a plate form intrusion. Actually, you can use this for when you're far from any boundaries. So you're deep somewhere in the rock. It doesn't mind if it is a paleo-magnetically interesting dike, or it is vertical or horizontal, because it's far from boundaries. So because the solution here assumes that you have an initial temperature which is homogeneous in the medium, and we are calculating just the changes. And the point is that we have a dike or intrusion which has the stiffness 2 times W, and it appears instantaneously like this, snapping your fingers, and it's there. And then with these boundary conditions, we can find a solution for this problem. And the temperature change created by this is then dependent on the original temperature difference between the dike and the medium. Its geometry, which is given here, its thermal properties, which is here in the square root, the diffusivity, and the time. And these are complementary error functions. Is the simple form of this FC. Now, this kind of a solution can be, if you take an example, you have a dike which is 2 meters thick. So W is 1 meter. Its intrusion temperature is 1000 degrees, and the surrounding medium is 0. Diffusivity is normal for rocks, and we can calculate that the temperature at the center of the dike, after 1 week, it's already down to 640 degrees. After 1 month, it's 340. After a year, it's 100 degrees. Now, this means that, like for paleomagnetic applications, the dikes are cooling very quickly. So it means that if they acquire a remanent magnetization during cooling, it takes place quickly, and therefore it's a good sampling medium for the magnetic studies. There are also characteristic parameters which can be provided for the half of the temperature and half of the maximum temperature cooling, and where the maximum temperature is reached at a certain distance, etc. But this is much more easily understood in an example like here. You can see this is a dike which intrudes close to the surface. It is originally 100 meters thick. In this graph, only 1/2 of that is given because it's symmetrical. And you can see that the ambient temperature is 0, and the intrusion temperature was 1200. So it's a mafic, ultramafic, well, let's call it a mafic dike coming to the surface. Now, the cooling after 1 year, 10 years, 30 years, 100 years, etc., goes like this. You can see there's a high temperatures, of course, in the dike itself, but at distances when we go outside the dike, the maximum temperatures are actually relatively mild. It means that the contact metamorphic areoles of a dike, depending on what kind of effect you're interested, can be defined when you draw an envelope curve for these solutions. And you calculate the maximum temperature at a given distance from the dike. You can see, you have a 100 meter thick dike at 200 meters away from the contact. At 1000 years, the temperature is increased by 200 degrees, but not more. So it's not really baking the whole environment. If this takes place in crystalline rocks, so any events, say less than about 400 degrees are practically not very dramatic manifestations. But this is the way to calculate the thermal effect of a dike. And because these solutions, like shown here, they can be added on top of each other by superposition. So you can also take this if you like, and if you have a problem with several dikes, you can calculate the thermal effects of many dikes and sum up the solutions from different dikes. So this provides a way to tailor a problem accordingly. Here is the same stuff, only the difference that now we have an idea that, okay, this is a dike coming to the Moho level, say at 600 degrees, and so it's a kind of underplating or that kind of an effect. And the good question is that underplating is often claimed to be a factor creating huge thermal effects in the crust. If you look now that you would have a 100 meter thick underplate coming at the Moho level, you can see that the thermal effect does not extend very far from the contact of the dike. Of course, you can make it bigger by making the dike bigger, but even then, it does not really change the situation very much. So the order of magnitude of some considerable effect of an underplate is geometrically constrained to about the range of the thickness of the dike. So you don't melt the complete lower crust easily with simply with dikes or an intrusion. Now, here is an example of a cooling intrusion, 1 kilometer thick intrusion as a layer, and away from the center of the dike. You can see these times in years. So it's typical diffusion thing. So it's first as a high anomaly, then the amplitude decreases quickly, and when the energy is diffusing out, so also the amplitude is getting lower and lower. You can calculate also the cooling rates and what is the host rock temperature, and these are direct tools for estimating the contact metamorphic effects. Oh, by the way, before I forget, I brought a couple of books for your attention, in the case you know already or don't know. And here is a nice compilation of applying physics to geodynamic problems of the Earth. This is by Kurt Stübe. And I think, Dave, do you remember, is this publicly available freely in the internet? So you can Google that and you would get it a free PDF copy of the book, which is nice. But be careful, it has a lot of printing errors. He even mentions that in his preface. But a free service is a free service anyway. Take the advantage. So it has a lot of physical applications to erosion, sedimentation, transport, paleoclimate, intrusions, metamorphism, and many things. So it's like a geology seen with the eyes of a physicist. More useful analytical solutions from the classical mathematical physical book on conduction problems, Karslow and Jaeger. You can find solutions of cooling bodies, which can be infinite plates. They can be a whole cylinder, or it can be a spherical body. The reason for this kind of geometries is that in physics, this kind of a simple geometries can be mathematically handled in a closed form, and they can be solved. Now, here we have a non-dimensional temperature, where the initial temperature of the cooling body was capital V, and the small v is the temperature at a given time. And here you have the non-dimensional distance from the center of the body. So we have distance x divided by the characteristic parameter, which here is the thickness of the plate. Here it would be the radius of the cylinder, and here is the radius of the sphere. You can apply this even like for kitchen problems. I have a steak. I take it from the oven at a temperature of 100 degrees. How long does it take until it's cooled to room temperature? Whatever. But you can use that also for calculating roughly the effect of cooling, like an intrusion, which is approximated by a spherical body, or this plate thing, which gives the same solutions as before for the plate-like intrusion. The cylinder is more geologically more challenging to apply, but it's possible. Now, and there, in this kind of things, presentations, there's a Fourier number, which is the parameter in these curves. So immediately you can calculate this Fourier number, which is diffusivity time divided by the square of this characteristic dimension of the system. And you can go back here and see which of the curves corresponds to my Fourier number, and see immediately what roughly would be the case. I think I have an example here. So if we have a dike which has a thickness of 2 kilometers, initial temperature 1000 degrees above the host rock, that's a diffusivity of 1. So we would have the curve number 5 when we calculate that. For the plate, it would be the curve number 5 here. It would be a relatively well cooled case already. But reading a value from here, and you can roughly see the temperature variation in and outside the body. Now, we have to be careful, of course. Now, these conductive models are approximations of the real nature, and the geometry is simplified. One of the things, like how far we are from the surface boundaries for the dike model, for instance, makes a difference in the final values. Be careful with that. And then when we start to look at like the real kind of emplacement of intrusions. Now, we have a lot of granitic intrusions in the crystalline rock. Have you ever thought of the mechanism? How do we bring kilometers thick masses of granite to the crust? Do we have a huge blob of magma somewhere at great depth? It just comes up like a balloon through the lithosphere and finds its place somewhere in the upper crust, and somehow throws the other rocks away? Or does it come as small pulses of magma? And both cases can be mathematically simulated. Here's once again a result by Chapman and Furlong. You have an idea that you have a kind of a dike coming at a sill, very thick one, comes at around 20 kilometer depth, comes instantaneously like this, and then we calculate the temperatures. So in the case that we bring all the high temperature rock in one intrusion, it would follow this curve. But if that would be divided into 10 intrusions, it would mean a prolonged heating and also a prolonged cooling time. So they also affect. And this is also very important in the case that if you think that you have a lithosphere where partial melting is taking place, like in the Himalayas today, and granites are improving to the surface. And finally, after some 10 million years, you can see, after erosion, you can see nice big batholiths. Did they come in one single package of melt, or did they come like this in small increments? The increment model is probably much more realistic, because the point is that if you create a partial melt at some depth, you remove material. Theoretically, the lithosphere could subside because something is removed. The melt comes up in a fracture or a fault or some sort of event, comes up, it fills a volume here. So basically, the lithosphere doesn't need to uplift or subside much at all if this system is working in small packages. This is probably following the kind of a name that nature is following. But if you look at like your contact metamorphic observations at different places, so the difference between 500 degrees and 650 degrees is a huge one in terms of metamorphic petrology. Okay. Then very shortly about paleoclimate. This is the simple idealistic case that the temperature varies linearly with depth. Of course, if thermoconductivity varies, you would have local variations of the gradient, but this would be the case in a steady state ideal lithosphere. Imagine that the surface surface temperature increases from this value T0 by climatic warming. What happens in the subsurface is, of course, once again, this is a diffusion signal which diffuses downwards in the rock and creates a disturbance. Now, once again, when you measure temperatures and gradients, you will get a transient situation. It's not a steady state. After a climatic warming, the near surface gradients are too low and they do not indicate the representative heat flow. This is the case we have here in northern European areas because of the glaciations. Then, on the other way around, if you have a climatic cooling, you would have this kind of a case. So immediately after cooling, you would see something like this going on. So the gradient would be anomalously high, and once again, it would not represent the reality. I'm not touching this too much because in low-temperature thermochronology, the methods we are discussing this week are related to much higher temperatures than the paleoclimatic temperature variations of the surface of the Earth, which is about, say, about plus minus 10 degrees or something like that, due to glaciations mostly. But these effects extend to several kilometers by diffusion. Had we thermochronometers that are able to reveal that, it would be really an interesting. And with Dave and with Lotta, we have done some pilot exercises on OSL and dreamed about cosmogenic isotopes as well. Now, we've spoken about extension, and now our basin is closing. The oceanic basin, the subduction ends, and everything is compressed together. This is like India and Asia, say about 30 million to 60 million years ago. The Tethys Ocean is closing, and as a result of that, crustal blocks are colliding, and they are not disappearing anywhere. They are thrusted on top of each other, and we have this kind of a imbrication or stacking of the crustal units takes place. And as a result of that, we create a much thicker crust. It could be 2 times thicker than originally. Now, as the crust always contains radioactive elements. So, and in the Fourier equation, the big capital A is an important parameter. The heat production is a very essential number controlling the temperatures in the crust and the lithosphere. In this kind of a processes, collisionally, we can even double the heat production in the system, because the mantle heat production is very low and doesn't really mean anything. But the excess heat creates heating of the stack. There's uplift. Always when there's uplift, there will be forces that start to erode the system down, and it erodes down, and the erosion removes actually heat production from the system, but it thins because it's getting thinner. But if the system goes in the normal style, after about 30 to say 50 million years after the collision, the conductive heating has increased the lower crustal temperature so much that typical crustal materials start to melt, and the dehydration melting of micas and hornblende produce granitic melts. And these granitic melts are then intubing to upper layers, and finally, after the cooling and equilibration and erosion closer to sea level, we have a kind of situations we see here, like in Fennoscandia. These granites you can see here by the bus stop in the road cuttings are actually this kind of orogenic granitoids, which were produced by thickening of the crust when the blocks from all the way from Ukraine to Fennoscandia met together and created a collisional frontier in southern Finland. Physically, we can break this down into elements looking like this. This is like children's block game. So we have 2 blocks meeting each other in a collision, and because the collision itself is a very fast, the plates are moving at a couple of centimeters or more per year. So geologically, the diffusion time is so long that we can assume that the stacking takes place instantaneously. It means that we can build this kind of a model where we have an initial geotherm, and the initial geotherm was in crust 1 and crust 2. Immediately after stacking, it would look like this. You have this sawtooth kind of a geotherm, but because this conduction takes place, this starts immediately, of course, to equilibrate, and it could be taking place like this. Now, this is a graph so that we would have this kind of a before the collision, this kind of a lithospheric pieces or crustal sections, and after collision we would have them on top of each other. It would be 2 times the original thickness. We get the original sawtooth geotherm, which then starts to equilibrate, and if we draw temperature, time, depth graphs of how the different pieces of rock in this kind of a system experience the temperature pressure changes, you would see this kind of a anti-clockwise metamorphic diagrams. And this is typical because it was a long time ago when people were speaking about Barrovian metamorphism and that kind of regional metamorphic events. It was possible to map from geological evidence, even without having any numbers yet, but it was possible to see that from the metamorphic facies variations and the barogenesis that the Barrovian metamorphism, which creates a thick crust, creates also this kind of a thermal pressure evolution of rocks. Now, when you start the evolution from somewhere there, first the stacking is immediate, down. We go down to high pressure, and then starts the thermal equilibration. But you can see that also the depth is decreasing. And this is due to the fact that the system is actually eroded at the same time. So the evolution of a metamorphic system of a collision, it's a competition between, say, the conductive heating up by radioactive heat and the simultaneous removal of heat sources by erosion. Because if we would not remove erosion from the system, it would overheat very quickly. It would get really, really hot. And therefore we get this kind of a loops, and this kind of a loops can be then traced qualitatively and quantitatively in metamorphic petrological studies of the rocks in the laboratory. And we can control that in terms of the physical models. Because see, the closer we are to the surface, the smaller is the loop. The deeper we go, the bigger is this loop. We have done this kind of a models for the Finnish geology. No need to go to those details here now. But then we jump to the second part of this class. Would you like to have a coffee break now or something? I think it would be. You're not sleeping. I'm happy. None of you is sleeping. But if you like, it would be good to jump up and get some fresh air and be back, say, 10 minutes. 5 past half 3. Would that be okay? Okay, let's do so.